Electronics in action.
Come on. I've been ordered to take you up to the bridge.
Hey, excuse me, which government owns this ship?
You watch this door. It's about to open again. I can tell by the intolerable air of smugness it suddenly generates.
Please enjoy your trip through this door.
Come on. Here I am, braying the sides of a planet, and they tell me to take you up to the bridge. Call that job satisfaction, 'cause I don't.
Well, maybe we'll never have robots quite like Marvin from Hitchhiker's Guide to the Galaxy. However, robots are an everyday part of many modern production lines, carrying out complicated jobs such as welding and spraying. Yet 30 years ago, there weren't any robots. The first industrial robot was built by the Unimation Company in America. And the man who built that first robot is still president of the company.
Well, the whole idea for the robot really was stimulated by Isaac Asimov, who's a pretty famous science fiction writer. He wrote a series of stories in the early 40s called I, Robot. And I was studying physics at the same time he was writing, and that sort of seeded my mind on robotics.
So what about the robots being built today? How have they developed from that first 1956 model?
The early model was pretty good as far as doing what it was designed to do, which is an industrial job, because we had studied many industrial jobs. But of course it used only single transistors instead of chips that we use today. It wasn't as reliable as a robot is today. We didn't have anywhere near as much knowledge of what to do in the field, and certainly nowhere near as much software.
This box contains a computer, and that controls the robot's movements. You could say the computer is the brains of the robot. The first design of computers forced Joe Engelberger to make some difficult decisions.
Now, when we started with a transistor that cost $1.70 a piece, and it was such a hard decision because we could have bought a radio tube, or I guess as English call it, a radio valve, for 30 cents. But some of us said, you know, I bet someday a transistor will be just as cheap as a radio valve. Now, today, you know that the function accomplished by a transistor only costs a small fraction of a penny. We never imagined that when we started.
Early computers used valves. Valves are electrical components which change the signals fed into them. In this case, the signal is being chopped in half. That's called rectification. But then along came the transistor. Transistors were faster and more reliable. The biggest use of early transistors was as amplifiers. Amplifiers changed the size of the electrical signals. Amplifiers are the basis of many electrical devices, especially things like radios. Radios used to have hundreds, even thousands of separate components, but now everything's getting smaller and smaller. The result is integrated circuits, chips, the latest wonder of the age. Thousands of transistors and other components squeezed onto a tiny piece of silicon. Once designers had the new microcomponents, they could begin to think of new things to do with them.
A synthesizer is a musical instrument, but because it's a very modern electronic musical instrument using lots of high technology, it gives us so much more control over the sound than we've ever had with any other previous musical instrument. The first requisite of any musical instrument is that it has to have something to make a sound. And the synthesizer has a part that vibrates, but electronically, so you can't actually see it moving like you can see the string of a guitar or the reed of a clarinet, but it does vibrate electronically, and it's called an oscillator.
The oscillator is an electrical circuit which produces regular signals. Oscillators can produce signals of different shapes. The different shapes can produce different types of sounds. The oscillator is connected to a keyboard. The keys trigger signals of different frequencies, different musical notes. What happens next?
The sound passes along the audio chain from the oscillator into the filter. And there we can modify the sound by softening off those sharp points on the oscilloscope. And the softer it becomes, so the softer we hear the tone.
The filter is another electrical circuit. It changes the shape of the signals, and that changes the tone.
The final stage in the audio chain is called an amplifier. And this determines the amplitude of the sound wave, or how big it is. And the bigger it is, the more of it we hear, so it's like a volume control.
So between them, the electrical circuits produce and shape the electrical signals.
We must behold the things we see.
At the moment, Ultravox are in the recording studio laying down the tracks for a new LP.
Can you stick a bit of sort of room sound on this, Jim?
Many of those tracks will be produced on one of the group's electronic instruments.
Can you give us 4 in there, kid? Well, stop playing tricks on me. Can we try it again from the top?
The milk bowl sound.
Ultravox have been using synthesizers for some time.
This synthesizer here is like one of the first synthesizers that was commercially available. I mean, it's quite an old one, but we still use them. They're very basic synthesizers. It's an analog synthesizer. It was developed by Dr. Robert Moog quite a few years ago. The problem with these things is this is the type of synthesizer we had when I joined the band at first, and when you play sort of hot, sweaty clubs, the things we got to tune all the time. It's basically a 3 oscillator synthesizer, so you can actually switch off one of the voices, one of the oscillators, and get a very thin sound, very normal, basic sound. But when you start adding the other oscillators, giving it a bit more depth and body, you can tune these things together. You hear it tuning into itself there. And this is the actual synth that we did, the sort of Vienna part on the bass part, you know. But I mean, these things now, you can't buy them now. I mean, technology's moved on far too much to sell people things like this anymore. It's actually an antique synthesizer now. You know, it's about 15 years old. We've moved on to this type of thing now, which is a German synthesizer. Actually, this synthesizer, when you create a sound on it, it sounds as though, although you've never heard the sound before, you never heard anything like the sound before, it sounds as though it should be an acoustic instrument because it has overtones. It's got 2,000 waveforms in it, so the actual waveforms can change when you play the sound, like a normal instrument would. And when you play one note on a piano, there's so many overtones and so many waves and forms inside that sound that this does the same type of thing, except you're making totally inhuman noises from it. Now what we've got in this this thing today, in this synthesizer, is me. I mean, that's me going ah. This particular instrument here, or any of these instruments, you can give to 20 different keyboard players, and they'll come up with 20 different types of sound and 20 different feels that a keyboard player could play. It does anything you want it to do. I mean, once you've actually written a song, then you've got to decide what type of sound you want to use to put this, the best way to put the song across.
This computer also plays music. But it doesn't use oscillators, filters, or amplifiers in the same way as synthesizers. In a computer, one of the most common uses of transistors is as switches. Switches may not seem very important, but if you have lots of them working on a string of noughts and ones, then you have a microprocessor. And that's at the heart of a computer. Computers are masses of high-speed transistor switches. But switches on their own aren't much use. First, the microprocessor needs an input circuit so it can receive messages. Messages from, say, the keyboard. The messages are then changed by the switches. Then the changed message is sent back to the outside through an output circuit, which might control, say, a TV screen. Different messages are produced by different patterns of switches. Those switch patterns are controlled by the memory. The memory contains the instructions about how the switches should be organized. But computers aren't the only devices which use microprocessors. Microchips are increasingly common in domestic appliances, which is perhaps no surprise when you discover how the older appliances worked.
Well, when the water boils, it obviously generates steam. And the steam is emitted from the body of the kettle through a very small hole, which is difficult to see, even on camera, just at the rear of the kettle. That steam then plays onto a bimetal here. The bimetal bends, in this case, backwards, so it then knocks that switch out. That switches off power to the kettle, very simply, de-energizes the element, and boiling is complete.
What are the problems with this type of switch?
Well, you can see there's obviously quite a number of pieces involved. The spring in the switch alone here has 3 components in it. The bimetal, although it looks a simple piece of componentry, is in fact very complicated to engineer and keep in constant sort of shape and position.
Recently, the older kettle has been replaced by an entirely new design. That brought further problems, as now the steam comes out a long way from the switch. It's not possible to use the old kind of mechanism, so what was the answer for this type of kettle?
Well, we decided, after a lot of thought, to go electronic. And that is, if you like, the equivalent section of the 2 products. Here, the steam, as I said, is generated at the top. It's sensed by a thermistor on the end of those 2 wires. The thermistor senses steam, and electronically now, with the aid of a microchip, it operates a relay, again shutting off the power.
The chip, the microprocessor, is a simpler version of the one inside a computer, but in this case there's an extra part, a sensor, the thermistor in the kettle. The thermistor senses the temperature of the water and sends back messages to the input. When the water's hot enough, the microprocessor will tell the output to turn off the kettle. Using chips has lots of advantages.
Well, there's only one component now to put in the kettle on the day-to-day assembly line. That, if you will, is, if you like, a kettle switch. And the assembly of this is fairly straightforward. It's everyday technology, isn't it?
Another advantage is that chip control is far more accurate. So can Dr. Moorcroft predict what might happen in the future?
Yeah, I think the wider use of microchips in domestic appliances. It must come, it must happen. And I think we've started something that has to continue.
Microprocessors in the form of computers have even found their way into medical diagnosis. One person in 100,000 may suffer from the disease leukemia. The difficulties of diagnosing leukemia are being tackled by the Imperial Cancer Research Fund.
Well, the problems are common to many diseases that doctors have to deal with, and that is that when the patient appears with an acute leukemia or some other form of leukemia, often it's not straightforward simply to say, these are the symptoms, we know this. The problem may be obscure, and simply trying to sort out the diagnosis from the information available in the clinic is not straightforward. So very often a doctor may decide that he would like to do some sort of laboratory test which will give him much more information about the particular condition that the patient is suffering from.
Diagnosing the disease, deciding whether the patient has leukemia or not, can't be done without the use of laboratory tests. The problem is that working out what the test results mean can be done only by somebody with a lot of experience. But those experienced people are in short supply. So John is developing a special type of computer program called an expert system, which should be able to do some of the sorting out.
In that instance, we can say unequivocally that it's the common variant or common subset of ALL.
The first job is to find out how the human expert does the diagnosing, then convert that into a set of rules for the computer expert system. What sort of things go into the computer's knowledge base, its memory?
First of all, the important facts about the subject. For example, measles is a disease is a kind of fact. Or we might want to put rules of thumb. Rules of thumb like, and this is not a very realistic medical example, but something simple like if the patient has spots and the patient has a temperature, then the patient may have measles. So if such and such symptoms, then such and such a diagnosis.
The computer asks a series of questions, starting with simple things like the age of the patient.
But then the computer is going to go on to some more difficult problems, what are called the cell lineage and the cell type. And this involves a series of questions to the user about the clinical diagnosis, what was the diagnosis that the doctor thought who sent the blood sample. I think the thing that really got a lot of people very interested, maybe even excited, when expert systems appeared on the scene, was that they were not simply able to do the job of diagnosis or whatever you're interested in, but they had a simple sort of ability to explain what they were doing as they did it. And here you can see on the screen a very simple example of that. The computer has asked a question. It said, what was the TDT result? This TDT being a particular lab test. What I decided to do was to find out why that particular question was being asked. And here it says, I'm trying to find out about this particular test to decide the sample cell lineage using the following rule. And then it prints out an if-then rule. If the TDT value is greater than 20%, then the cell lineage is acute lymphocytic leukemia.
Expert systems guide the inexperienced doctor through complicated problems.
And a few more questions, and then finally it makes a diagnosis and prints out the results for the cell type, the cell lineage, and the suggested diagnosis for the patient. Now that could also be printed on paper and sent off in the post to the doctor who sent the sample. But some people see this as much broader than that. It's not simply a matter of helping people make particular special decisions in medicine, but it's allowing us to look at whole new classes of decision and problem that we've never been able to before. In traditional science, the emphasis has always been on what can we measure? How can we do this mathematically? How can we make decisions or solve problems in a quantitative way? What expert systems, or really the discipline behind it, the subject behind it, artificial intelligence provides, may be the ability to solve problems which are more qualitative kind, which depend more on experience and judgment and rules of thumb.
And then, of course, I've got this terrible pain in all the diodes down my left side.
Really?
Oh, yes. I mean, I've asked for them to be replaced, but no one ever listens.
I can imagine.